Welcome to the ACIT Science Podcast, the official podcast of the Association for Critical and Interdisciplinary Thinking. We are a global non-profit organization dedicated to spreading education around artificial intelligence, neuroscience, and social change. In this podcast, we are hoping to provide insightful discussions with young professionals and world-leading researchers alike. I'm your host, Manuel Brenner, and now, without any further ado, let's jump right in.
Yeah.
I'm here with Bea.
Hi.
Thanks for being on the podcast.
Yeah, thanks for having me.
So before we dive into what your research is about and what you focus on during your days as a researcher, can you just give a short introduction of who you are and kind of what brought you into the field you are currently working in?
I will try my best. So I'm Beatrice. I'm in Heidelberg and here I'm doing a Ph.D. in climate science. What brought me there? I think it's curiosity in the end. I think curiosity is what brought me to physics, and then I had the chance to work in different parts of physics and get to know different methods, especially from the theoretical and computational physics, and now with my current research topic, which is climate variability. I found a perfect match of both theory and computational physics, data science, and in the end it's my curiosity into these things that brought me there.
So you mentioned climate variability, which is like your overall research topic. So can you give like a short maybe like overview or definition of what climate variability is and how it ties in with climate change and kind of the day-to-day variability we see in the weather?
Yeah, exactly. So you've been mentioning already one part of variability, which is the day-to-day variability. So that's maybe the most intuitive way to understand variability, because there is the day and the night, and there's a temperature shift in between these two, simply driven by the orbital configuration of the Earth surrounding the Sun. So this is one part of variability, but there's also variability on other time scales. So now one could go from the diurnal to the annual cycle, for example. So temperatures, for example, here in Central Europe, warmer in summer compared to winter. But then there are also other changes on longer time scales. So for example, there is the El Niño Southern Oscillation, which brings harsh weather conditions to large parts of South America every 6 or 7 years. So and this continues on and on up to the Milankovitch cycles, which are again orbitally driven environmental conditions that distinguish between warm and cold periods, for example. So you can define climate variability on all time scales, and the same also on all spatial scales. And in the end, it just describes how climate is fluctuating around a certain mean.
When you say orbital variability, do you mean the position of Earth with respect to the Sun or other planets?
Yeah, exactly. So on the very long time scales, this is really given by the, one calls this, for example, obliquity or eccentricity of the Earth compared to its orbit. This leads to major changes in the insolation of or the solar irradiation. So, for example, ice ages or warm periods can emerge.
Okay, so this can have quite a dramatic effect on the climate, actually.
Yeah, indeed. Yeah.
So maybe to already move into the area of climate change skeptics. So as you mentioned, you have these large-scale trends that can also cause pretty dramatic shifts in the climate on Earth. Like sun activity, for example, we probably can talk about a couple of things. So how can you determine that climate change right now is mostly caused by humans and by emissions that are caused by human beings? And how can you untangle the changes through other effects from these like committed by human beings?
Yeah, so the most simple answer to that is that we observe this huge agreement between the greenhouse gas effect and what it does to our climate models and the instrumental record. So we cannot explain what we observe at the moment in our records. Like records is just we measure the temperature outside, for example.
Right.
We cannot explain that without the human-made CO2 emissions. So this is, I think, the most simplest and clearest answer to that question. Of course, there are certain difficulties in attributing, for example, single events to the anthropogenic warming, but overall the rise in the global mean temperature is well understood by scientists, and we see this from all kinds of records and the models, and we cannot explain it with these other mechanisms that are brought up by skeptics. So
it's pretty like the increase in the velocity of the change is a pretty strong indicator that it's actually caused by human beings, because there's no other causal effect we could think of that would have this outcome.
Yeah, I'd say this is the most intuitive way to understand it, but of course there's strong scientific evidence that this is not the only fingerprint. We can definitely assign today's shift in the mean temperature to our greenhouse gas emissions.
And so you are analyzing long-term climate models, which go back also thousands of years, and analyze like the change in climate across like these shifts between ice ages, for example, and the climate we see today. And you're trying to understand from that how the changes brought about by climate change that we are observing right now is going to change like certain properties of climate on Earth. Can you elaborate a bit more on what kind of changes you are expecting climate change to bring about, and where the uncertainties lie as to what it's going to bring?
So this is really a topic of ongoing research. So maybe let's start right from the beginning. So first of all, we have to clarify a few scientific questions. So, for example, whether climate variability depends on the mean state. So, whether a shift in the mean temperature leads to shifts in the variability. This is, for example, one question one could address to these very long natural archives from ice cores or from speleotems, and by analyzing these time series, we can learn a lot. So the goal is to learn from the past, to take these lessons for the future. So there are, so this is, for example, one major question that needs to be answered: the dependency of variability on the mean. But there are also others. So, for example, how variability changes on different time scales and different spatial scales. That's also not that clear yet. Also, one can think of variability of the global mean temperature, but then there is variability of local temperature records, or variability of precipitation. And so this is a huge topic, and it's hard to say variability is going to change like this with global warming, but there are, for example, indication that short-term variability, such as the occurrence of extremes, that they're going to change with global warming.
Maybe to clarify a bit what the difference between mean and variability is, and why that's such an important question, is to think about like a room temperature of your living room is probably like 20 degrees, and it's going to be 20 degrees in winter and in summer. But if you go to a place like Siberia, for example, you can have a mean temperature of like, 10 degrees, but in summer it's 40 degrees, and in winter it's minus 40 degrees. That probably doesn't add up when you do the math, but like so the variability is what's causing these extreme events like droughts and extreme colds and extreme storms. So the fact itself that the Earth is going to, the mean temperature on the Earth is going to increase by 1 degree might not be as bad, but so you're saying that these changes in variability is what we need to understand, because that's what's going to matter in the long run.
Yeah, exactly. Those have like big socio-economic impacts. Also, a shift in the mean temperature has big impacts just because of all these tipping points, for example. But in the end, how it affects us humans, it's mostly in form of extreme events, or in the duration of a heat wave, for example, in mega droughts and or very strong rainfall. And this is then what has like big impact on, for example, the food supply. So yeah, I would definitely say that it's at least as important as the mean.
Okay. You mentioned tipping points. Are you referring to kind of these like points of no return when some kind of feedback mechanism kicks in and we can't go back?
Yeah, exactly. Yeah. So we physicists we prefer the term feedback. Yeah, because in the end, I mean, the Earth is like exists for a very, very long time, and we as a human species live here only for a short time. So in the end, these tipping points will probably turn out to be feedbacks. But there's also research going into this. But yeah, let's say it's feedbacks. So for example, there is the Arctic. So it could, there is a certain probability that we're going to lose the Arctic ice sheet, and this would be then, to large part irreversible on a certain time scale. So that's why people tend to call it tipping points. And it makes like the picture I have of them is also more like the one of a tipping point, but to describe them physically, you would better call it feedback loops.
So what's the difference between a tipping point and feedback loop?
Like for me, a tipping point is like this. At the moment you cross that point, you're gonna lose the state of the art. Let's say so. If you've lost the Arctic ice sheet once, it's gone forever. But a feedback loop is for me some mechanism that triggers another one, and so on and so forth. And in the end, this could go back. So it's more reversible if it's a feedback loop. Yeah, it's more reversible, but the question is, these types of feedback loops that we are triggering right now, they are probably reversible on time scales that are longer than the lifespan of humans. So of a human being, or just of mankind in general, or like that's hard to say. So I don't know the numbers exactly, but there has been studies of the Arctic ice sheet that, like in a certain greenhouse gas emission scenario, we're probably gonna lose it even longer than the time when we would expect the next ice age. So there are these studies ongoing saying, okay, we're going to postpone the next ice age by thousands of years. So but I cannot estimate on the lifespan of humans. Sure. I mean, it's kind of also what you're researching, right? Yeah. So because you're looking at timescales of like how. Like maybe to explain the concept of a time scale in general. Can you elaborate a bit on that? Yeah. It's such a natural thing for a physicist to say, but I don't think. Yeah, that's true. Our climate system, it covers almost all time scales that are that we as humans can observe. So there are turbulences in the air on the timescales of seconds. Then there are atmospheric mechanisms on the timescales of hours or days or months, and then you have ocean currents that act on timescales of years or decades, and then you have these orbital changes on 10,000 of years, and this goes back up to the geological time series, so time scale. So those time scales on which, for example, continents form. So that's the beauty of our climate system, that all these time scales are coupled and that they exist. Which makes it a bit complicated, though.
Yeah. So if you want to build a model of climate, you have to maybe have an aim to look for short-term effects or mid-term effects, but in the best case, if it's a really realistic model, you want to get all the timescales right.
Yeah, well, all of them would be computational very hard, but let's maybe focus on those models that predict our today's climate, and also that compute the scenarios based on certain greenhouse gas emissions for the future. So those models usually cover the last 1,000 to 2,000 years. We call this the common era. And of course, you would like to have them being right on the hourly scale as well as on the centennial scale. And that's actually what I'm currently working on. So I'm comparing the performance with regard to variability on these longer time scales, like decades to centuries, in order to investigate whether they actually perform well there with respect to variability. So for those models, of course, you would prefer something that performs equally on all these time scales.
Yeah, but I guess you have a research question and also like a more application-oriented idea that it's really crucial to get the next 10 years or 50 years right. So that's what you're focusing on.
So with respect to predictions of the mean, for example, also of local temperatures or rainfall, they might perform very well. I'm more interested whether they get the physics right. So if they get the right projections for the right reasons, because one can think of the dynamics on these timescales arising from a coupling of all subsystems of our climate system. So, for example, the atmosphere is coupled with the ocean, is coupled with the cryosphere, and so on and so forth. And there are feedback loops in between them, and nonlinear interactions, and all of them adds up to a variability. So, and of course, this is difficult to simulate in a model, because there you have a restriction on your degrees of freedom, simply because we're limited by our computing capacities. So it's very important to understand the main physics that governs this interplay of different subsystems, right, in order to incorporate them also into the models. And so these models, they are being constantly updated, and they are getting better and better over the years. And so some of them, for example, they have already dynamic vegetations, others have very evolved ocean dynamics. So in the end, we're improving them and hopefully get the best possible image of our Earth.
So to get a bit more technical, you have these models that were developed by other groups, or maybe also people in your research group, which are these large-scale collaborations between many different groups, so some working on getting the ocean currents right, and some others the cloud formation and the atmosphere. And then you generate data, or you make predictions with these models, and then you take a look at these predictions and analyze them and try to figure out how good these predictions are. Is that correct?
It's almost correct. So indeed, I'm not a modeler, so I'm not working on the models itself. I'm just taking the data. So I very much rely on the work of other researchers, and I'm very grateful that indeed there is this international, very colorful community and large corporations. I'm very grateful for that. So yeah, but what we do in our research group in Heidelberg, we are more investigating the past climate indeed. So it's not about future projections, but about how we can, let's say, benchmark also the models with climate from the past. So we are taking paleo data from natural archives, such as ice cores or speleotemes, and from this way we construct temperatures, and then we use the models to simulate the past. So we take the model runs for the past 2,000 years, and then we compare it to the paleo data in order to verify whether the models are, whether they agree or whether they differ, and if they differ, like where do they differ, and so by this we hope to get better insights into the Earth dynamics.
So, like a problem you always encounter with the weather is, I guess, this kind of unpredictability. So you say that the models need to capture something underlying the fluctuations you observe in, like, on a daily basis, which is kind of something deeper and like hidden beneath the fluctuations you observe on the surface. So in like the whole concept of chaotic dynamics and chaos theory was also developed around there, like by Edward Lorenz, who was actually trying to model the weather. And so the basic problem of chaotic systems is that if you start at a certain place, you really don't know where you're going to end up, because even very small fluctuations in the state, like in your initial state, will completely dramatically change where you end up in the last place. So obviously you can't, when you have these climate models, really rely on judging the quality of your reconstruction, like, or the quality of your predictions by like looking at the actual perfect fit between what's happening and what you predicted. So what are different variables you're looking at, or like different quantities that can actually show you that you did a good job at reconstruction the climate of the last 2,000 years?
So yeah, so you're absolutely right about the limit in the weather prediction. So there's this weather prediction limit of like something like between 11 and 14 days, and it's largely due to the turbulences and the chaotic behavior of our atmosphere. As for the models, well, I'm not a modeler, but as far as I understood, is that they do like pre-runs where they equilibrate their simulation, so to say, in order to get the initial conditions right. But yes, they are quite sensitive to the initial conditions. And I think there are numerical ways to prevent such a chaotic behavior. But of course, it's more difficult to simulate non-linear behavior than linear behavior. That's also my suspicion why on the very long time scales they could perform or could provide too low variability. So that's actually the starting point of our current research. So yeah, big question is how nonlinear our climate is on certain timescales. And
can you say that this nonlinearity is caused by these feedback loops and feedback effects, that they can kind of throw the whole system far off linear and predictable behavior?
Yes, certainly. So these feedback loops are definitely leading to some nonlinearities. That's the main idea behind that. However, it's not completely clear which kind of stochastic processes can be used best for describing these climate signals. So there are many candidates, also ranging from long range memory processes, over to simply autoregressive processes. So to which degree they are linear or non-linear, it's difficult to judge, but of course we have these feedback loops, and they definitely add non-linear effects to it.
Yeah. And do you have to kind of understand them properly to be able to judge the kind of variability you're going to face in the long run?
Yeah, exactly. So that's also why I'm focusing on analyzing these time series in the spectral domain. I mean, we as physicists, we love the Fourier space anyways, because so many things get much simpler if you Fourier transform them. But yeah, the idea is by looking at the spectrum of climate variables to really identify the processes that govern variability or the fluctuations. So, for example, by describing them as power laws or other types of mathematical laws. And you can also see the periodicities, for example, as strong peaks. And yeah, by this you can identify certain modes, such as the Nino-Southern oscillation, which I've been mentioning. So, yeah, but this is also like state-of-the-art research, but I think looking onto these timescales from different point of views, especially also from the spectral domain, can help to get insights into the processes.
Okay. Is there a more like specific example of you observing certain like signature in the spectrum and kind of tying that to an underlying process that's like or is it like too naive a question to phrase it that way?
So to link it to a certain process, that's now quite difficult, but what you can certainly observe is that, for example, on timescales where there are more turbulences, you observe a stronger scaling, for example. So stronger scaling coefficients, which means like more nonlinearities. Whereas in, for example, in temperature, in a region where the temperature is rather stable and you have like just some white noise, so it's like the signal has some wiggles, but it's equally distributed, for example, then you would observe a flat spectrum. So there's no scaling because there's no memory in the process. It's just like every signal is kind of randomly distributed around the mean. So that's something you can observe, definitely.
So you can distinguish between signal and noise, and the signal is in best case trying to like telling you something meaningful, and the noise
or you can say that this climate variable behaves like noise, or this variable has some memories, for example.
We mentioned before we started recording, we talked also a bit about this whole idea of having these time series signals and doing spectral analysis, and you said that most of the methods you are using are either coming from plasma physics or from neuroscience. So there's this kind of universality behind the methods you're using to analyze the climate and the methods you could in principle use to analyze something completely different. So during your master you also worked in a pretty different area of many-body physics. Can you maybe talk a bit about what you did there and kind of how like this kind of universality behind the methods physicists use kind of allowed you to change field, and it's kind of behind like everything we do as physicists or as scientists.
Yeah, sure. So first of all, that's with the literature. It's partly true. It's mostly the more evolved spectral methods I'm trying to get into. There was large progress in plasma physics a couple of years ago, working on wavelets, and now I observed the same in neuroscience, that there are also higher order spectral methods. But of course there are also many methods that are used for many years in climate science, and I'm using them as well. But, so this was more referring to the new literature. But yeah, so before I was working in the field of quantum simulation, and on one of my first days in my group as a PhD student, one of my colleagues said to me, yeah, well, when you understood one simulation, you can understand every other simulation. And this is also what gave me confidence, because what I was doing before is I had, like, let's say a box in my head with many boxes inside the big box, and then there were like particles sitting in there, and those particles were like close to the coldest temperature on Earth, and then these particles were talking to each other, and we could give them, let's say, we could hit them a bit, like give them a quench, that's how we call it in physics, and then dynamics evolved. And then I was looking at this dynamics. And in the end now, what I'm doing with climate is quite similar. The climate is also kind of modeled in these types of boxes that talk to each other, and then you give a certain forcing to some part of the system, and then this evolves, and in the end you're looking at the response. Yeah. So, and yeah, indeed, the theoretical physics, it gives you all the tools that you need to understand these types of complex systems. So, and that's what I like about it, because you have these, let's say, universal theories like linear response theory, which you can observe in basically every system that exhibits some physical phenomena. Yeah. So it wasn't, of course I had to get into the literature, but in the end, to get from one topic to the other wasn't a big deal. Yeah. Yeah.
So is that what maybe like fascinates you most about working in this kind of field and doing this theoretical work? Also, what is most appealing for you about this kind of approaches and going about research, like from this perspective?
So most appealing to me is that you can always learn something more. Yeah, I love that, because you can. Yeah, every day you find something new. And besides that, you're learning quite some useful skills as well. Yeah, not only, of course, there's always a challenge to your mind. You're always thinking about something. That's something I like. But then also the simple coding, it's a nice practice, and you're getting better. The same with writing, science. The more you read, the more you write, the better you get into both.
Talking about writing, you are also interested in science communication, and also started writing for Many Body Physics, the blog that we are also collaborating with, and Alex from our first episode is also part of. And you also recently wrote a book for Springer, or in collaboration with Springer, about quantum simulations. So how did that whole project come about, and what motivated you to go the step to write something like a popular science book, and to tell as many people as you can about quantum computing and simulation?
Yeah, it was happening by chance. So first of all, I had the chance to join the blog Many Body Physics by Alex and Oscar, two friends of mine, simply because we shared lunch together at the Institute of Theoretical Physics in Heidelberg, and then I was writing an article for another magazine, and somehow we were talking about it over lunch, and then Oscar told me, we have this blog, and I said, well, what blog? Yeah, the big logo on our door. Okay, and then it became apparent to me that there was this blog, and they did amazing stuff also with their drawings, and of course I wanted to jump in. So this was kind of my way into communicating about quantum physics. And then with Springer, it was a similar occasion. On a conference, I talked to a woman who was working for Springer, and I was asking, I'm writing these articles for our blog and also for another magazine, so maybe I could write something for you as well, just a simple article. And she said, yeah, well, like, send me an email, and I did so, and I waited 4 months. And there was no respondence, but then after quite some time, a person found my CV and also one draft of an article, and she called me, and she asked me whether I want to write a book.
Okay. That's nice.
I was quite surprised, but I agreed apparently.
Yeah, nice.
Yeah.
So how long did it take you to write that book, and how did you go about like writing a book?
So this book was more like a small ebook. It's 50 pages. The main idea is that if you want to go from Heidelberg to Berlin by train, then you can get into quantum computing rather easy. Yeah. So that was the main idea.
Okay.
And I liked also the approach of saying, okay, there's lots of literature on the market, but we really want to focus on the math, on the algorithms, on the code, and really give some simple examples, but explain them in a good way, so that people can understand this black box of a quantum computer. And then the writing process was easy going, to be honest. So
really, yeah.
I had also one month of a break in between the masters and the PhD, but I got married in this month.
Nice. Congrats.
So it was like in between having the wedding and some honeymoon and writing the book, and then I had the first chapter written back then, and then I think over Christmas I wrote another one, and then over Easter I wrote another chapter, and then that was it. So it's mainly 3 chapters, and then I handed in mid of this year, and it came out in September, and it's selling quite well. I'm really surprised. I still don't believe that this is my book, but
because the imposter syndrome is always kicking in.
Yeah, but the working together with Springer was a unique opportunity. I'm very, very grateful for that, and I had great support from their side.
Yeah, it's a really cool project. So is it aimed at a scientist audience or physicist audience, or can even like lay people get into it?
Yeah, it's aimed at people interested in quantum mechanics.
Okay.
But the main idea is to address, let's say, students in their first year in math, in computer science, biology, chemistry, physics, of course, as well, because quantum computers probably will be used not only by physicists, but especially the first application seems to be simulation of chemical reactions, or development of medicine or vaccines and so on. So the idea was to give like students in these type of subjects insights into quantum computing.
Now you've written a book, it might maybe if you get into science communication feel a bit weird that if you're just starting out with your research are already like actively communicating, but considering I'm also recording podcasts, I also think it's really crucial that people that are not too far advanced in their career are already like stepping in and trying to communicate science actively, just in their everyday life, and also kind of trying to actively seek out opportunities to communicate science. So is there kind of this deep underlying motivation for you to spread science across kind of across society, and like do you want to actively continue pursuing this science communication, or is it more that you just like what you're doing and wanted to share it with a couple of friends?
Yeah. I think it's more the latter, but I understand very much that there are these strong motivations behind communicating science, and I appreciate them. So for me in the beginning it was really just fun, and that's why I did it. Well, also with the book, for example, it's maybe not so common to publish a book after your master's, and some people ask me, wow, okay, that's a huge step, you know. And for me it feels more like I had the chance to study quantum physics in my master's in Heidelberg for 2 years. I was thinking about quantum physics every day for 2 years, so of course I could write 50 pages about the quantum computer. It sounds maybe a bit weird, but I was studying this for 2 years, and if it's fun to me to write about it, then why not? And besides that, we learned as a physicist to research in literature and to base our science on the knowledge of others, and so it was mainly fun to me, but also I had this feeling of that I wanted to share what I learned. And this feeling now becomes stronger also with being more involved in climate science, because here I see also a duty of scientists to communicate what we are going to be faced with. Because if you take, for example, the current situation of the pandemic, it would be a weird situation whether the virologists, for example, debate whether they should communicate their science or not. So we as climate scientists, we have this monopoly of knowledge. Of course, also other people can read about it, and there are other disciplines doing the research, but in the end we have the facts on our tables every day. So if we don't inform the public, then who's gonna do it? So I can definitely understand this feeling of many people that they are getting more involved into science communication because of this, and I have the same feeling for my work at the moment.
Maybe would you say it's even like kind of becoming a duty for scientists to step up, because sometimes it can feel like, as a scientist, I mean, there's this cliche of that being this remote world, like academia in general and theoretical physics, maybe also more specifically, of being this remote, shut-off place where you kind of get lost in your models and in your mathematics. But especially with climate science, but in general with the state of the world we are currently in and the changes that are coming, I think that it's really becoming this kind of duty of scientists to also like step out of academia into society and really face that responsibility of like really representing what we believe and what we think is necessary.
I don't have such a strong opinion on that. Maybe because I'm not that professional. I'm still just a PhD student, so I can understand professors, for example, that say when I go to a protest, I'm going there privately, and when I communicate science, then I'm doing that professionally. So I've never thought too much about that. So whether scientists could go more into the direction of policy or not. I think if we're doing our job well, if we're doing research well and communicate it well, so that not only our colleagues can understand it, but also others, we are also taking the responsibility, because we're funded by the public. So we should definitely give that back to the public and not just share among us scientists, so to say. How we give it back to society, whether we go into parties or to protest, or whether we just communicate the science in an understandable way, I don't have a strong opinion on that, to be honest. Maybe it's something for each and everybody to decide.
Probably. I also don't have a strong opinion. Just curious to know, because sometimes it can feel like this whole idea of inaction being kind of the same thing as action. Like, I mean, if you're don't act in a certain way, you kind of also, that's also a kind of action. And if you're, if we're at that tipping point, like in these kind of feedback mechanisms, and if you have the feeling that you know more than many other people, and if you're in a position of, then I think that you could argue that there's this natural sense of responsibility that should come with that, and maybe that should incentivize you to really seek out that public, or I mean, there's many different roles to play, like not only science communication, but also like taking action politically, for example.
Yeah, definitely. And the least we can, and from my opinion we should do, is explain the things in such a way that they don't remain black boxes, so that the quantum computer isn't a black box, or viruses, or climate models, because in the end maybe this is a major factor for people to trust scientists when they know their methods and the reliability. Maybe they trust them more, for example, or these kind of things. So or maybe they are not so vulnerable to fake news and these kind of things.
Yeah, that's true. Like getting away from this black box idea of science being so complicated that you cannot understand anything about it, so you don't even need to try. And that seems to be like the kind of the approach to thinking about science for a lot of people. And I think we should be able to get away from that, because it's just not true. And you don't really need to like be a professional scientist before you can kind of understand the most important points of what is going on. Yeah,
definitely. And also what's important to me is that like I would like to live in a colorful society, and so it would be nice if not only the privileged people like that we are, we've been studying physics both in Heidelberg, it's a privilege definitely, so that not only we are talking about science which is affecting everybody, for example the climate, so I would like to have like more exchange of the scientific community with society, and also to lower the barriers for people to get into these fields.
Yeah. Now that you've spent a couple of years working as a researcher, do you have if you have like any big lessons that you've learned, or like any like important insights that you have gained in the first years of your working as a scientist, that you would, if you could talk to yourself maybe 4 years ago or 3 years ago, do you have any advice for yourself?
Yeah, I think I do. So, well, I've just finished my first year of a PhD, but I've been always working as a research assistant, so from the beginning of my studies, and I was always changing fields. And sometimes I dropped an offer which was quite appealing, but I dropped it because I had more fun doing something, doing other things. So that's definitely something I would tell myself, that I should just trust in that feeling. And sometimes it's good to also turn directions and get into something new, although the old offer might be nice as well, but that's so today I'm very, very grateful for these experiences from the different fields.
And maybe it also teaches you that you shouldn't be too worried about being able to get into a new field, because like deep down there's certain things you have learned that you can apply in the new field, and that can maybe even provide you a wider perspective on the new field you're getting into.
Yeah, exactly. It was rather the other way around. So, for example, in in my master thesis, I wrote about a concept which was called quantum Fisher information, which I got to learn before in my work as a research assistant, where I was working on microscopes, but where we were measuring Fisher information. So I took the Fisher information from there to my master thesis, talking about quantum Fisher information and linear response theory. And then I took the linear response theory to my PhD now. So it's rather nice to have these links in between these points, which seem to be unrelated.
You worked on microscopes. You mentioned you worked with Stefan Hell in the research group. Was it before he got the Nobel Prize?
No, it was afterwards.
Okay.
It was afterwards. I think it was one of the main reasons why he, I'm not sure, but he was moving from one department to another, and I had the chance to be part of this moving process, and we really moved microscopes from one building to the other, and it was great fun because they are so sensible, and it was fun. It was like by this you really get to know the instruments and you get to understand them.
So you had to build them, like deconstruct them and then move them and then build them.
Not all of them, but certain parts, and or new microscopes were delivered, or there was much more space in the new building, so we just built new microscopes. Or this was of course a work of a PhD student, but I could help with it, and it was an interesting time there.
Nice. And that was the technology that he got the Nobel Prize for. This
stat microscopy. Exactly. It's it's a certain microscope with a very typical laser technique, and you can resolve nanometers, which is very, very small.
Nice. So we've talked about science a lot. Maybe to in the end, to take a step back from the pure science, you are also like actively playing a lot of music and are a jazz pianist. So how do science and art go together for you, or would you say art is kind of a way to relax from science, or are they kind of two facets of the same thing for you?
Many people say that there are so many physicists or mathematicians that play music, and there must be a relation, and you have to think complex, and to be honest, I never felt this connection of science with music. I just never felt it. For me, playing piano is really just about interacting with others and about emotions. So I try not to think when playing the piano. That's the opposite when doing science. It's interesting, And but of course, it's also that's why I love the jazz music. It's just happening in the moment, and you react spontaneously.
It actually feels like very different from like what you do as a scientist. I mean, you're kind of trying to find some more permanent truth and insight, and in jazz it's like everything is up in the air and everything is communication.
Exactly.
But sometimes, like, if you're really engaged, I mean, there are these flow states, for example, you've probably heard about them. That, like, if you're meaningfully engaged in any kind of activity, you might enter these same kind of states of like being really losing track of time and losing track of everything, and just being really focused on what you're doing right now. So I guess for me, that would be the relationship between science and music, and maybe also like the more general view that they are both pretty complex, and it also sometimes it feels like playing around with complexity. That seems to be something that human beings really enjoy doing.
That's
on that brink of complexity.
That's true, because physicists we always reduce complexity, right?
But
and maybe playing the piano is the same. I never thought about it.
Do you have a favorite jazz pianist?
Oh yeah, Bill Evans.
Ah, for sure.
Yeah.
And that we agree. Yeah.
Okay, nice. Do you have a favorite physicist?
And there's cliche answers like Richard Feynman, for example, and Einstein. I mean, they are obviously extremely fascinating characters. I found Heisenberg's autobiography pretty impressive. I don't know if there are any physicists alive. I mean, we tend to glorify the past a little bit. Like idols can be more easily found in the past, like the distant past, that we don't have as much information, as much insights into. I don't know. Do you have a favorite living physicist or scientist in general?
Living, no. My favorite scientist, Anderson, he died in end of March, but age 93 or something like that. He was pretty old.
I didn't even know he was still alive, to be honest.
But a living physicist, maybe Sachdev. He did quite some stuff in theoretical physics. But yeah, I'm not. No, I'm not that informed. No.
Yeah.
But I like the Heisenberg biography as well.
Yeah. And he's also a pianist.
Yeah, that's true.
There are apparently recordings of Mozart piano concertos with him playing.
Oh, interesting. Yeah.
Yeah. But I never found them. I tried to hunt them down, but never found them. Yeah. Maybe as a last question, if there's like any research question that you could have answered right on the spot, like the answer to a long unsolved mystery in science or physics specifically, what would it be? Do you have anything in mind?
Oh, for this I will have to think about it.
That's a good physicist answer.
For sure there's something. Not very much related to what I'm working on, but what I'm truly interested in is whether these high temperature superconductors will work one day.
Did you listen to the podcast with Alex?
Not entirely.
Because in the end I asked that question and that was his response as well.
Okay.
So, it seems to be. Yeah.
Interesting. Yeah.
Yeah, but it's.
But yeah, I mean, if this is gonna happen in the next whatever years, I mean, if we could experience that still, it would be amazing.
Yeah.
And it could also solve some of our climate issues.
Yeah, it's really something not a lot of people really talk about. I feel like that hasn't really entered the general public perception of things we are hoping for or waiting for.
Yeah, indeed.
Maybe it's too complicated or too abstract.
Well, but electricity is not that abstract.
Yeah, that's true. But it just comes out of the wall for most people. I don't know.
Yeah, maybe because for the non-scientific community it sounds like very far away and not feasible.
Yeah. Maybe to come back with a even more last question after the last question, because you just said that would be important for climate change potentially, how would these superconductors, do you think they could have an impact on climate change or like our chances of getting renewable energies going?
Well, to be honest, no, they're not gonna help us with that because so if we look at the scenarios for the next 50 to 100 years, we will have to reduce greenhouse gas emissions now.
Yeah.
And we don't have the superconductors
That's
now available.
Okay, yeah.
So they will come too late for sure. So this was maybe yeah, the reaction was too spontaneously, but they're not gonna solve our anthropogenic heating now at the moment. Yeah, definitely not. Yeah.
Maybe like a pessimistic ending, but still, thanks a lot for being on the podcast. Really interesting conversation.
Yeah, thanks for having me. It was fun. Yeah.